just something a little cleaner that's doesn't have stuff that's happening in the background, okay? All right, so this new circuit will look like this. What can I torture you, inspire you with now? How about one of these? How about a series parallel? Okay, series parallel. And so here, I'm going to do something a little different. Node A, node B. And I'm going to number these R1, R2, R3, R4. Make this 18 source. While you're copying that down, I'm going to go ahead and do a VIR chart here. R4, R3, R2, R3. Could somebody mute their microphone because we can all hear the noise that's in the background, please?
Mr. Bolito, if you can mute your button.
Thank you. That's very helpful.
Christian, if you can mute your button.
Cool. All right, let me give you some ohms to think about. Let's go ahead and make R1 1.8 kilo ohms. Let's make R2 980 ohms. Let's make R3 220 ohms. It's a little hard to read, I apologize. Let me fix that for us. Will be 220 omega. And let's make R4 850 ohms. So that compels us to be very, very careful how we fill in our chart. So our chart will be filled in with R1 1.8 kilo ohms, R2 is 980 ohms, R3 is 220 ohms, and R4 is 850 ohms. Our voltage source is 18 volts. And our circuit polarities are negative, positive. Yeah, get used to looking at things from a variety of different perspectives. All right. So we stated earlier that we have a process for analysis. And that process for analysis is called what class? Circuit reduction. And the how requires us to do what? Redraw the circuits. And then the why is to simplify. So we're going to redraw this particular guy. And as we redraw this, I said you can draw it to the left, right, anywhere you want. I find it very helpful to draw them immediately below the original circuit, and I keep any identifying landmarks to stay in the same place. So I clearly will retain a point A. I clearly will retain a point B. I clearly will retain my voltage source, negative plate on top. This comes up to here. This guy comes down to here. Now, how do I approach my circuit reduction? How do I approach redrawing this? Before we parted company, I made a suggestion, and that was wherever you see the voltage source, put your eyeball at some point farthest away from the voltage source. So we may choose to put our eyeball from this perspective looking in. And if our eyeball is at this perspective looking in, we see a wire. What do we see on that wire? This end of the wire goes and attaches to node A. What's on this end of the wire? A resistor. And then it attaches to node B. Is there anything else on that wire between A and B other than the one resistor?
Nope.
Nope, not at all. Okay, so there's no series resistor here that I can combine with it, no series resistor here that I can combine with it. What do I do? Who's got a suggestion? Raise their hand. Or call your name out.
And you combine it with R2?
Who's offering that suggestion?
Christian?
Christian. Okay, Mr. Cortez, how would we combine it with R2? Do you see a relationship between R1 and R2?
Parallel?
Is everybody in agreement that R1 is in parallel with R2? Are they truly in parallel with each other? What makes them in parallel? Do you remember the definition for parallel? Components are in parallel if and only if the wires on one side of these devices meet at one common node. So do the upper leads meet at node A?
Yes.
Do the lower wires meet at point B?
Yes.
Yes. Therefore, R1 and R2 clearly are in parallel with each other, yes?
Yes.
So I should be able to simplify these two guys into a single equivalent resistance. And let's call that simple equivalent resistance. We'll draw that here. We'll call this REQ1. And that was equal to R1 in parallel with R2. Yes, that's the relationship that gives us REQ1. And then what happens between point A and the source? Nothing other than to copy an original circuit resistor here, R3, and copy this original circuit resistor here, R4. R4 is 850 ohms. This is still 18 volts, and this is still 220 ohms right there.
Those two are
And the
parallel too.
polarity is, that's an interesting observation. Is R3 in parallel with R4?
Yes.
Again, let's check the definition for parallel. The left-hand lead of R3 is it connected with the left-hand lead of R4 at one common node?
No.
No, because there's a resistor in the way, right?
Yeah.
Is the right-hand lead of R3 and the right-hand lead of R4, are they connected to a common node? No, I've got a voltage source in the way. So although they're drawn in a four-square box and geometrically they are parallel to each other, they are not, however, electronically parallel to each other according to our definition. Are we clear on that?
Yes.
Okay, that's, and again, whatever ideas come to mind, bring them out. Don't be shy, because we learn from these observations. You have an observation, you throw it out there, and if it's right, great. If it's wrong, it's still great, because you're thinking, and that's what I want to have, is the mind is working. So we leave R3 as in its original position, and we leave R4 in its original position, because they don't have a parallel relationship at this point that allows us to do any combination. So this is a good redraw to take us from 4 resistors now down to 3 resistors. So far, so good?
Yes.
We now need to redraw this again. We need to bring this down to a single resistance. We need to bring it down to an R total. So do you see a relationship between these components that we can bring down to an R total?
They're all in series now.
They're all in series. There is only one current path here for the electricity to flow, from the negative through R3, through EQ1, through here, through here. So we should be able to redraw this to become here. This is an 18-volt source, and this will become a single resistance, and this will become R total. Node A is gone, node B is gone. They've disappeared because they were existing between R3 and R1. They're now no longer part of our drawing. Let me say this. You need to calculate the parallel relationship between 1.8K and 980. So hopefully you have done that. You can use product over sum, or you can use reciprocal method. Whichever method you choose is okay, but let's see what you come up with in your calculation. So REQ1 will be your 1800 in parallel with 980. So your keystroke sequence was 1800 reciprocal plus 980 reciprocal equals, and you hit your reciprocal key one more time, and you hit equals one more time. And I'm looking for the first digit of that parallel relationship.
6.
Who gave me the 6?
Andrew.
Andrew gave me the 6. 6 is correct. I'm looking for the second digit. Somebody?
Rebecca, 3.
Rebecca? It is a 3 is correct. Who's got the third digit?
4.
4, who gave me that?
Kyle.
Kyle, good. All right. Now I'm looking for the digit after the decimal point. Who's got that?
It's a number 5. After
It's a number 5. Very good. Thank you, Pauline. Now I'm looking for the second digit after the decimal point. Somebody give me that.
3.
And that's a 3. And we follow that with an omega. So is everybody okay that this value works out to be 634.53 ohms? Yes? So far, so good? All right. So now do we have enough information to calculate an R total? We simply take this number that's on our calculator and hit plus 220 plus 850. And Mr. Bolito,
Yes.
what is your total, sir?
Let's see.
Do you have that for us yet? Yes or no?
No.
Okay, Mr. Lau, do you have a total for us?
2.05.
Mr. Lau? Pedro, do you have a number for us?
1.7 kilo ohms.
1.7, and what would be the digit after the 7, my friend?
0.
Would be a 0, correct. Kilo ohms, 1.70 kilo ohms. Any questions about that value? We will fill that in here. 1.70 kilo ohms. Very good. All right, this is nice. So what do we do from here? Yes, we want to mark our polarities. This is positive, this is negative, and electrons are flowing this way, like so, like so. So we have a total voltage, we have totals. The only thing left to calculate here is total current. And here we're going to remind ourselves with Ohm's law, V, I, and R. If I am looking for the I simply cover that part with my finger, and I'm going to take V and divide by R. Yes, so the 18 will be divided by the number we have in our calculator. So we will do this. 18 divided by this number, divide by this number. Okay, I am looking for total current. Somebody give me the first digit.
1.
1 is correct. A second digit, somebody?
0,
0 is good. Somebody give me a third digit.
5,
5 is good. How about the second digit after the decimal point?
9.
Is none.
Oh, 9.
9.
Wrote it down wrong.
Oh,
I got it. Really? I got a 6. How many other ones get 6? Okay, let's do it this way and show you how that came about. Let's do 18 divided by 1.7 second exponent 3. Oh, I see what happened. All right, let me show you what happens on the calculator. If we do the number that you see rounded here, 18 divided by 1700, same thing, you will end up with a 10.59. What I have here is there's a whole lot more information to our current. Our current, our total ohms. Our total ohms, instead of 1.7 kilo, instead of 1700, actually is up here. It's 1704.5. So it has a bunch of giblets. So what I end up doing on my calculator is I do 18 like you all are doing. I hit divide like you all are doing. But instead of typing in 1700, I have the ability to pop up here and capture the calculation from before, bring it down. So I have all the digits and the giblets after the 1.7 kilo. And now if I hit enter, I end up with a 10.56. So I will keep the 10.56 on here, but I will certainly accept the 10.59 milliamps. So write down 10.59 milliamps, so 10.59 milliamps. But that's why there's a slight difference between your calculator result and mine. And we could be a couple hundredths of a decimal off. We're okay. All right. So does everybody understand how there's a difference between my calculations and yours? Has to do with the ability of this calculator to be able to capture a number from a previous calculation with all of the digits and implement that in a subsequent calculation. Okay. All right, cool. We now have a total current, and I will write down here 10.59 milliamps, okay, just to be consistent with all of you. All right. Wow, we still have 8 boxes to fill. So just because we found one current, have we found them all?
No.
No, because the original circuit is not a simple series circuit. However, what do we happen to have in the middle in our drawings? We happen to have a nice series circuit right here. So if we take this information from our most recent redraw and transfer it up here, we know the current leaving the source is 10.59 milliamps. We know the current coming back to the source has to be 10.59 milliamps. And the current going through, down through REQ1 is also 10.59 milliamps. So we have 10.59 flowing throughout this series circuit. Does this 10.59 milliamps happen to flow through any series components in this circuit? It flows through each of these series components, because that's in series, that's in series, that's in series. And what do we know is the same in a series circuit is the current. So do you now have two currents that we can fill in on our chart? Which
Yeah,
two
we can
currents?
put it for I.
Well, we're filling in I, yes. We have 4 squares to fill in, but what are we going to fill in where? Which one of these cells am I going to fill in?
All
R3
of
and
them.
R4.
R3 and R4.
Oh, R3,
R3 and
R4.
R4, yes. This is my 10.59 milliamps here, and I have 10.59 milliamps here. I cannot fill in 10.59 for R1 and R2 because R1 and R2,
Are different.
they split the current. Because if I take this information from here back up to my original circuit, my 10.59 milliamps that leaves the source does indeed flow through 3. But what happens when it hits node A? It splits. So part of that current proceeds to R1, part of that current splits down to R2. That current through R1 will come down, loop around, go to node B. The current through R2 will come down through R2 into node B, and they recombine to give us the 10.59 milliamps back to the source. So we need to understand that the current through R1 and R2 are not 10.59 because it splits at node A and it recombines at node B. So we cannot fill in this chart with 10.59. That being said, how do I find the rest of these currents?
Current divider formula.
I would go with current divider formula, sure, that would be good. So let's go ahead and reiterate our methods of analysis. So at this point, we would have, for suggestion, CDF, current divider formula, where IRX is equal to RT over RX times I. So how do I implement current divider formula to find how much current flows into each of these branches? What numbers do I use in this particular formula? So let me give you a for example. If I was looking for IR1 is equal to something over R1 times the total current, what is this numerator going to be? It says RT because this is the general form of the formula. Do I use the RT for the circuit? Do I use the 1.7 k ohms?
No.
No. What should I use in place of RT? What should be the numerator?
634.53.
Precisely. I need to use the RT for only these two guys in parallel. These two guys in parallel came out to be named REQ1, which was the 634.53. So this particular numerator has to be REQ1. And if I go to fill this in now, my IR1 is equal to the 634.53 over 800 times 10.59 milliamps. Those are the numbers that you're going to use. The RT is not the RT for the entire circuit of 1.7K. The RT is only the RT for these two guys in parallel, which was REQ1, which was 634.53. So I'd like everybody to do this calculation. 634.53 divided by 1800 times 10.59. I will do it as well. So I have that number from before, which I will use. Enter and divide by 1800. Enter and then multiply by that current. And I have a current. So IR1, who would like to call out the first digit, please?
3.
3 is good for the first digit, decimal point. Who would like to call the next digit after the decimal point?
7.
7 is correct. And who would like to call the next digit after the decimal point?
3.
Works out to be a 3. How many people agree with 3?
Yes.
Okay,
Yes, I agree.
milliamps. All right. I'm going to write down 3.73 milliamps. I end up with a 3.72 milliamps. It's okay. We have a slight difference. That's not going to be a problem. So are we in agreement? We have a current here, and I'll write down what you all calculated, 3.73 milliamps. Everybody good with that? Cool. Actually, use a darker color. 3.73 milliamps. All right. So I have a question for you. We have one more current here. How many of you would use this method for IR2? IR2 is the next calculation. So how many of you would take the 1059 and subtract the 7.33 in order to get what's left over for the current for this branch?
I would.
It's going to be the
First time.
Mm-hmm. Mm-hmm.
3. I think you just gave us the answer.
No, I didn't give you the answer. 7.3, excuse me. Bleh. No. There, yes, I did. Somebody, I came pretty close to giving me the answer. But that's my dyslexia. I see 3.73, but I read it as 7.3. Anyway, I apologize. So how many of you would have taken the 10.59 and subtracted this number to get what's left over, which is something in the 7 milliamp range? You could do that, but I don't recommend that, and here's the reason why. If this was an error, taking the original current and subtracting an error will give you another error. My recommendation is to use current divider again, calculate a new number, and then add the two currents to see if they add up to be the total. Let's go ahead and proceed on this basis. This will become 634.53 over, what do I have here, 980, and then multiply by the 10.59 milliamps. So let's go ahead and generate IR2. Calculate using current divider what this number ought to be. So again, I will do it my way. Enter, divide by 980, and then multiply by this, and I get a current. Pretty close. Pretty close. All right. Who would like to call out the first digit, please?
6.
6 is correct. And who would like to call out the second? It would be an 8. And how about the digit after the 8?
6.
How many people agree with the 6?
Three.
I agree.
Okay, 6 milliamps. Okay. And I end up with a 6.84 milliamps. That's okay. We're a few hundredths off. That's not a big deal. I'm happy that you all are in agreement with each other. So we have a branch current here of 6.86 milliamps. And when these two currents come together, the 3.73 milliamps combines with the 6.86 milliamps, does that up to be your 10.59? Exactly. Okay. So your numbers are spot on there and there based on your rounded answers. Cool. Is the last column easy to calculate? Bingo. It's nothing more than voltage is equal to, remember, voltage on our Ohm's law, voltage is equal to I times R. So here's your I, multiply by the R, will get you these voltages. So go ahead and calculate current times ohms, current times ohms, current times ohms, and calculate each of those voltages. And I will check your numbers in a moment. I will calculate the same. Dun, dun, dun. Then enter times O. And enter times 0.8. Cool. All right, plus, enter, plus, enter, and it adds up to 18. Yay, this is good. All right. Okay, I'm calling out for VR1. Mr. Lau, do you have a value for VR1, sir? Wenbin? Yes or no? Pedro, do you have a value for VR1, sir?
6.71 volts.
So you end up with 6.71 volts. How many people agree?
Yes.
Yes.
I agree.
I agree.
All right, I end up with 6.70, but that's okay. All right, and the voltage for VR2, question goes to Rolando.
Not ready yet.
Not ready yet. Okay, question goes to Pedro.
6.72 volts.
6.71 volts. That's where it should round. I end up, again, because I've got super memory, 6.70. If you're off by 100th, it's okay. Should these voltages be the same, my friends?
Yes.
They should be the same because isn't R1 in parallel with R2? What do you know is the same on parallel branches of a parallel circuit? The voltages have to be the same. My 6.71 volts here has to be the same as the 6.71 volts here because they're in parallel. So they should appear here as well. How about the VR3? VR3, Pauline, what do you have?
I got 2.33 volts.
2.33 volts. How many people agree?
Yes.
Okay, 2.33 volts. I get 2.32. That's fine. And Rebecca, do you have a VR4, please?
9.00 volts.
How many people agree with 9.00?
I agree.
Yes.
I agree.
I agree.
9.00 volts. Cool. I ended up with an 8.98. All right, we're just
R1, I got 671, and then R2, I got 672.
Yeah, that's okay. Yeah, if we're a hundredth of a decimal place off, that's fine. Yeah, if you learn to use the memories of your calculator, the most correct answer is 6.70 and 6.70, 2.32 and 8.98. But if you're within hundredths of any of these values, the 6.72, I would certainly accept that. Yeah, 2.33 and 9.00 would certainly accept that. Good, this is great. And that didn't take, well, the actual analysis on paper took a bit of time, but the important lesson to learn here is the method. That given a series parallel circuit, we have a process for analysis. That process is called circuit reduction. How do we do this? We use redrawing of circuits. Why? To simplify. And we have simplified this step by step from 4 resistors down to 3 resistors down to 1 resistor. And then we did our analysis here and took our information back up, okay? So the worksheets that you're going to be receiving for the parallel series and the series parallel worksheets will be similar kinds of circuits to these. The voltage sources may be a little different, located in different places. So here was our parallel series, and we may see the voltage source in a different place, but the analysis is still going to be the same method. If you follow these steps and do the VIR chart and look at the different methods of the calculations, then you'll be able to work things out just fine. Building this in Tina is going to be super fast and easy. So without doing the explanation, I'm going to come down here and I'm going to share, and let's see how fast I can pace through this. Dink and share. Okay, now you see my Tina screen. I'm going to do I'm just going to do a file new. That's fine. And I'm going to take this guy, put it over here, and I'm going to rotate this bump twice. So I have the negative side facing up. I'm going to take a resistor and put this over here, rotate this. That's got to be my R1. R1 is going to be over here. Put this over here, rotate my R2. It's going to be here. Take this guy, put it over here. That's going to be my R3. Take this, put this guy over here. It's going to be my R4. Okay, now change the ohms on this guy to 1800. So 1800 and enter. And change this guy to 980, 980 and enter. Change this guy to 220, 220 and enter. And change this guy to, what did I say, 850. So 850 and enter. All right, let's connect some wires. This guy will come up to here, go to here. This guy will come up and connect there. This guy will come down to here to connect there. This guy will come down to here, connect there. This guy will come over to here to connect. This guy will come down to here and connect. Okay, looks like it's all connected. Oh, I got to change the voltage source. Voltage source goes to 18 volts. Okay, now do all my values match? Analysis, DC, table of results. Boom. Do I have my 3.72 milliamps that I called out? Do I have the 6.84 milliamps that I called out? Do I have the 10.56 milliamps and 10.56 milliamps that I called out? Do I have 6.70, 6.70, 2.32, and 8.98 that I called out before? Yes. So all of your numbers are within hundredths of these measurements, yes?
Yes, I do
Cool.
have a question.
Please.
So being that there's some hundreds of difference, should we consider the third digit after the decimal instead of the second digit? just to come as close as possible.
No. Just stay doing what you're doing, because showing everybody how to use memory on their individual calculators is a monumental task. And that's fundamentally what it takes is learning how to use the memory of your calculators in order to get your values to be spot on with iCalculate and what the simulator generates as a full DC analysis. Doing what you guys are doing is just fine. You can be within a few hundredths of a decimal place. I'm completely okay with that. If you want to explore, take the time to explore how to use the memory of your calculator, we can take that as a offline, and I'll be happy to discuss that with you all individually. On some calculators, it's easier than others. On some calculators, you already have a memory position 1, 2, 3, 4. Some have 1, 2, 3, 4, 5, 6. Some have a memory A, B, C, D, E, F. 6 memory cells, and they're labeled A in alphabetical order, A through F. So depending upon the memory system of your calculator, you can have calculations that are easily spot on the same as mine, as well as what the simulator shows. But I'm not going to require that of everybody, because it is, and I've done it before, tried to do it before with like 10 different calculators, how to show 10 different people on 10 different calculators how to use the memory. It's just easier to say, let's just use the rounded numbers and get something that's really close. And since we're within a few hundredths of a decimal place, we're really close. As an instructor, I can't be really close. I have to be anal, and I have to generate numbers that I'm accustomed to with the standard that I've held for myself in the past. And I'm compelled to use memory as often as I can, any way I can. That's why I choose to do this. So that's a long way of answering your question, Pauline, I'm sorry, but did that answer your question?
Yes, thank you.
Okay, yeah. Being a few hundredths off on these numbers right here is perfectly fine. So guess what? I built one. Guess what I'm going to do? File, save as. Okay, except now this is a series-parallel. And this is a 4 resistor, so 4R. So I have a parallel series 4R, and now I have a series parallel 4R, and I'm building up my library of circuits.